hard to read out. So our research focuses on the atomic structure analysis of all sorts of nanomaterials. And today I'm going to focus all the work we did on semiconductor nanomaterials, more specifically the defects analysis in semiconductor nanomaterials. So I'm just going to kick off here. So for semiconductor nanocrystals, just a quick intro. Light-emitting tiny crystalline particles, with size below 100 nanometers. It has applications in photovoltaic, thermal, electric, light emitting, and so on. And when we mainly made these nanoparticles through colloidal synthesis. So besides the semiconductor itself, it is capped with a layer of organic capping ligands that's from the synthesis process. And we focused on making these nanocrystals with more complex structures, such as this one, polytypic structure, which means in the one crystal entity, it has two different types of crystal faces in the structure. So basically, the structure is made more complex, so we can tune the band gap structure and band gap energy. And this is what they call band gap tuning. Another thing you can do to tune the band gap structure and make the structure even more complex is to add in different elements. This is the multi-elemental system of these nanocrystals. So in this example, I have copper, tin, zinc, tin as elements in them. So as you can see, the copper, zinc, tin would be the cationic elements in it, and ionic element is selenium in this structure. So all the structures I will present later on would have this elemental composition. Sorry, I'm a little bit sick today. And so why do we want to study the defects of nanocrystals? So defects can significantly impact its properties, apparently, because with such a small size, defects, especially continuous defects, would take quite a large ratio of the atoms within the total atoms. And this is an example showing quite rich tuning defects in the zinc blende nanocrystal. And it needs to be controlled in the application because it changes the carrier dynamics significantly, especially it induces non-radioactive recombination and reduces mechanical strength and so on. But it can also be utilized as the examples I showed before. You can actually use this defects to change the direction of crystal growth and to design them into more complicated shapes. And it is widely used in semicon, as you know, the N-type, P-type doping. And it has localized states that can be used in quantum computing devices. And then, these defects can act as active sites for catalysis reactions as well. So that's why we need to study them, but I'm not going too deep into the application as we are mainly doing structural research. So, so this is a tetrapod nano crystal. So some defects can be easily detected, like these ones, with a simple TEM image. This is the atomic resolution image. Most of the time, you don't need such high resolution, just some fringe resolution images. You can already see the defects by a mapping, a dilation mapping. You can see the more blue region area would be the more compressed region, has a more compact atomic packing. And these color changes between the boundaries means the crystal faces are actually changing. These are different crystal faces throughout the structure. And we can easily mark them out. Then I blow up this part to show the defects more clearly. So the purple is Wortzat structure, and the blue is zinc blende structure. So clearly, this tiny nanocrystal is actually consisted of two different types of structures. And we can build models based on the structure and do further analysis. But some defects in nanocrystals are not as easy to detect. So this is an example of another crystal that we made. It has this perfect single crystal looking appearance, but is it as innocent as it seems to be? I presented in the second part of the presentation. So the first part is still about these obvious defects that can break the crystalline continuity. This is a blow up of the zinc blende twinning defects. As you can see, the crystal structure is not continuous. In these parts, so the structures would form a twinning, which means they are mirroring along the plane, which is the twinning plane. And then it is clear that the crystal growth direction, the structure direction follows, is altered by the twinning boundary as well, which makes it definitely not a single crystal. And another common type of defects we can see is the stacking faults defects. I again marked different crystal faces with different colors. So you can see the zinc blende has a typical AA stacking, meaning every layer has the same crystal arrangement. For the Wortzat, it has AB stacking. So this layer is different from like this layer. And this is how we distinguish different crystals. And then the crystal growth transition would follow zinc blende Wortzat, and then zinc blende again. And with these defects and different crystal phase transition, the structure path would be again different. So this is very important for people who study charge carrier dynamics. And then this is a new type of twinning that we recently discovered. It's going to be submitted in our publication next month, I think. So this is a Wortzat twinning boundary that we haven't seen it reported before. So between these two Wortzat boundaries, they measure along this line. This is an interesting structure because in semiconductor nanocrystals, because the size is so small, most of these boundary being forced to deform are in core shell structure when they have a core shell atomic structure mismatch. But these structures on the left and right, they would have exact same chemical composition. And the formation of this part of the structure, you see this part being compressed, is because of the mismatch between the red region and the green region to compress this part further. I'll show it here. So this region, triangle region, would be the zinc blende. It has an angle of 70.5 degree. And if they are not compressed together, the Wortzat structures, they would have an angle of 70.1 degree. So it's smaller than the wedge that's lodged into it. That's how this deformation forms. This is important again because different from these structures that also defected, but the structure is relaxed and free from compression or dilation. This part of long defects actually not relaxed. So for people doing simulation, there will be a big difference in the charge carrier transportation mechanism. And so we go back again to the first part to detect these crystalline defects that are more difficult to detect. So is this particle actually a single crystal? From this image and from XRD analysis, we may reach an easy and direct conclusion to say yes, but it is actually not as simple as this. This concept is first brought out by people doing this research here. We cited them here. So in this seemingly single crystal looking crystal, there are actually different domains with different chemical composition and different atomic arrangements. But if you remove all the contrast difference in the map, you see them looking like single crystal. The reason is that the defects, although they are there, they actually only arise from the chemical arrangement difference within the atoms. The crystalline structure, which is the Bravais lattice, they actually don't interfere with the Bravais lattice continuity. So it would still be a single crystal if you do not consider these elements being different. So if I say this is all just silicon, it would be a single crystal. But unfortunately, there are a lot different chemical elements in them. So they would be not actually a single crystal. We observed this in many of our own nanocrystals. So this is, again, the tetrapod nanocrystal. Oh, maybe I should show the schematic earlier. So this is a 3D nanoparticle structure with a middle core and four like arms. So the middle core would have a different crystal structure with four arms on the outside. And this is an ADF image of this structure. From here, we can easily see the contrast of different atoms are different, meaning they are actually not the same element. And depending on how these different elements arrange themselves, there are different domains that has different arrangements. So for example, the domain 1 in this part has an atomic arrangement of this with corresponding atomic structure, and domain 2, domain 3, domain 4, domain 5. So these different domains would effectively make them not a single crystal. And it's in a recent paper just published this month saying that the influence of this structure on the property, especially the band gap behavior of this material, is actually as significant as your, say, different crystal phases. We observe this very often in other crystals and in other directions as well. And this is an intensity mapping of all these atoms there. And based on these intensity maps, we were able to build atomic models. So based on the Nature Communication paper, we further developed the research in this field. And then when we concluded that one nanocrystal actually can have many different domains, although they look like a single crystal. And then these different domains would, because they have different atomic arrangements, right? They would have like very complex space group names like this. I don't think many people would find these names very interesting, except people who do hardcore crystallography. So we found a way actually to further simplify and understand this structure. So with this structure, they look quite different, but their atomic structure arrangement is actually the same. The difference would be in the color arrangement, which is the cationic arrangement. So in the first three, we can actually still see they belong to the zinc blende group. And in last two, they still belong to the Wurtzite group, although they have completely different names in crystallography. This is because when you change the elements, the mathematical definition of the smallest unit cell that defines this structure changed. It doesn't mean the structure actually changed that much. So I'll further elucidate with another example. So, for this unit cell, it only has two elements, which belongs to the space group Wurtzite. It is like very different from this space group that belongs to monoclinic crystal group. You would think the structures are not related to each other at all, just looking at the crystallography. But when you actually build a bulk model, or you actually have the material in hand to do experiment, to image them on TEM, you see they're actually related, deeply related, in a way that they have many equivalent facets. Their crystal structure arrangement actually do not change that much. It's only when you incorporate more elements into the system, the smallest unit to define the system has to expand and change to describe this more complex structure. But in the essence, it hasn't changed that much as the conventional crystallography made us believe. And then based on this kind of discovery, we further classified all the space groups that are commonly used in semiconductor into two groups and 5 subgroups to help people image them, analyze the structure better. And based on that reclassification, we summarized there are some directions that can be used for chemical identification, meaning that if you image this crystal from certain direction, the final projection patterns you generate from the imaging would be periodic, analyzable. And there's non-chemically identifying direction, meaning if you see from the projection direction, all the elements, they kind of align in the projection line, so they all contribute to the final projection signal. Then you actually cannot use this direction to analyze your crystal. This is an kind of end result, experimental result from these two type of analysis. So this is chemical identifying. So there are a clear periodicity in the structure, and you can easily know on these positions, the elements are heavier in comparison with the rest of the element position. But here, there's actually not much you can get from this this image, because this is imaged from direction that's not suitable for the analysis. And because the atomic arrangement is closely correlated with the nanocrystal shape, we actually summarized how to analyze nanocrystals with different shapes from specific angle. For the cubic shaped nanocrystal, the analysis angle is actually from the top, or from a 70.5 degree to the top face, and so on. There are other summaries here, but it basically follows the rule that we summarized in this slide. And we also have a handbook summarized to show the equivalency between different crystals. So this is this is the basic structure of maybe over 58 more complex structures you will see in semiconductor nanocrystals. And this handbook that we're going to publish soon will help you to identify these more complex nanocrystals from simple crystal order arrangements. And yeah, so basically that's a part of our group study focused on the atomic structure analysis, and especially the defects analysis of semiconductor nanocrystals. And thank you for for your time to hear this.